very glad everybody is basically decided to stick with this. It's a good sign. I want to go over a few business things before we get back into our story here. Most of you seem to have found your way onto Moodle and have picked up the classes, the quizzes and the assignments and stuff. Were there any questions about the assignments or the workshop or anything like that that other people might want to hear the answers to? Anything? Yeah.
Every Sunday.
Yeah, try to get it done by Saturday night. I'll do some grading on Sunday usually. That's right. Yeah. So you have, just to remind everybody, you're going to have basically two quizzes, one for the workshop, one for the reading. And then there's a little 2-minute video every week as well. Make sense? I enjoyed meeting you. One more thing to say about those videos too. So if you do an assignment late, like one of the quizzes, they will auto-update. They're sort of scored automatically, so that's fine. If you submit a video after, like Saturday night, essentially, you need to email me. And I'll accept your late videos all semester long. So if you forget to do one, turn it in. I'll probably knock a point off or something like that for turning it in late. But you have to email me because I won't know that it's sitting there and needs to be graded otherwise. And it'll just be a 0 on your account, whatever, your grading sheet there. Does that make sense? So email me, send me a link to the video, and I'll grade it and update your grade if you're late on those. What else? So, any questions, concerns? Another thing, big part of this grade is a big part of your grade, a reasonable part of your grade is discussion, participation. If you miss a class, you don't have to email me that you're sick or you're stuck on the toilet or whatever. Just don't email me that stuff. I'm not that kind of a doctor. But do watch the lectures. I post them on YouTube. They're linked in the syllabus. Watch the lecture that you missed. Send me some deep thoughts and be prepared to talk about it at the beginning of class when you come back. Does that make sense? So along those lines, the way that I do this is I just kind of have a spreadsheet over here, and I have all your names on it. And at the beginning of class, I'm going to kind of ask you guys in general what sort of concerns or questions that you have from last class, anything you went home and thought about. Maybe if you don't have anything like that, just to remind us what we talked about a little bit, and I'll use that to make sure that everybody has a chance to talk. And I'll kind of, if what I do is I go through this list. If I've made it through the list and you're not volunteering, I'll probably just call on people randomly. That's just how it works. So that's how I make sure everybody's talking. So please make this a conversation. Stop me as I'm talking. It's not fun for me to just sit here and yammer. But there is a story to be unfolded, and I want to guide you through that. But I want to get feedback, and I want to hear from you guys as we're going. So please continue to talk. Make this a discussion. Don't make this a full 100% lecture. It's really boring for me if that's how it turns out. All right, enough of that, I think. Yeah, any questions, anything about that? Why don't we go ahead then and just recap what we talked about last week, other than basic introductions and stuff. And until I learn your guys' names, please tell me your name when you when I call on you. Somebody want to kick it off? Yes, sir.
I was curious, Andrew.
Andrew. Oh, okay, yeah. Hey, Andrew. Very cool.
And you mentioned something in passing very quickly in the previous lecture.
Yeah.
That you don't think that science can describe everything.
Yeah, that's great. Let's talk about that. I think I probably said that I'm not sure that science can explain everything. Yeah, and so there's a huge bifurcation between descriptions and explanations, and I'm going to build that out a little bit today, but that's a really good point.
I guess my question was like, if not, then, I mean, isn't that the point?
I think that we live in an age where we have a lot of hope that scientists can do the job that many other people have done in the past. And so I don't profess to have like the definitive answer here, but I see that, to preview, I think I want to get into this a little bit, particularly the difference between what a description and an explanation are, because oftentimes I think that we accept descriptions as explanations in science. I'll make sense of that more in a second. One little blind spot, though, that I see that I don't know if it can be reconciled is that science is only capable of even potentially explaining things that it can reproducibly generate. So a phenomenon that you can basically reconstruct and everybody can agree that it's happening. So what do you do with things that aren't necessarily reproducible? That's really tricky. So give me an example. How about something that happened one time in the deep past? Very, very tricky, right? Now you can amass evidence for an argument, much like a court case, right? You can maybe make a really convincing argument for how you think that this one-time event went down in the past. Let's say the formation of the planets. We're going to be talking about those. As your technological power increases, you might actually be able to see things that look a lot like planetary formations elsewhere. You might be able to see solar systems even. We'll look at some of those later in the course. So you might be able to strengthen your conviction that what you're seeing is congruent with this event in the past. But at the end of the day, it's very tricky to talk about those things. And so, science is a wonderful method for ruling out things that don't make any sense, for sure. But there's a whole other host of things in that bucket of difficult to reproduce. Like experiences are very difficult to reproduce and to convey, right? So you often see like the social sciences, the psychological sciences, they're often under fire because the studies that they often project into the world, people have real difficulty reproducing the events in a lot of these studies. And so they're often in the crosshairs for this reproducibility crisis that you'll hear about from time to time. And I don't think it's necessarily because they're not methodologically sound. It's often that they're trying to get at something that's deeply inside of us, and it's very difficult to talk about that. So, yeah, long story. I mean, there's much more to say about this, and I think that we'll peel it back as we go forward. I am just not wholly personally convinced yet. Maybe you guys will talk me out of this. That science is capable of addressing everything in the room that's happening right here today, for instance. I think there's a very high level abstraction in human society. You might call it culture or motivation or spirituality or whatever. There's things going on inside of us that science has a really hard time with. And there might be better approaches than science to understanding and organizing those features. I don't know. It's something we'll keep coming back on. Yeah, Dante, right?
Yeah, Dante. You brought up how can we reproduce something that can only happen once in the past? As someone studying archaeology and history, especially like anthropology, this question happens a lot.
Oh yeah.
That this occurred.
Yeah.
When it's and it's not like with the strong where we can physically look far enough in the past where we can observe
Yeah.
backwards.
Yeah. Yeah.
You can't do that.
Yeah, it's rough. It's really rough.
What you can do with science is use something else that's happened to predict what's going to happen or what what could have happened in the past. If something is similar,
Yeah.
say, well, extrapolating from that.
Yeah, absolutely. I mean, you can be very powerful. I think you just have to be really careful with this concept of certainty at all times, right? I think that we got in this last time, if you'll recall, talking about the motivational structures that lead people to pursue ideas sometimes for their entire lifetime that end up getting overturned. And you might think, how in the world could somebody study something for 50, 40, 50 years and be completely wrong about it? And you have to be very careful how much certainty you place in your own theoretical understanding of reality. At the end of the day, new evidence can arise for any number of things that we've been absolutely certain of in the past. This does happen. The textbook loves to make an example of the Copernican revolution, where we went from thinking that this Earth was at the center of the universe to thinking the sun was. We'll deal with that story more in depth, but that's just a famous example of something that happens all the time in science, actually. Now, the history of the Earth and the planet and all of this is really, really difficult to make sense of. And I think that's something that will make light of as we go through these planetary stories. The story we tell about our own planet has changed radically just in the last 100 years. It's changing right now. You know, this idea that you guys probably all grew up with the idea that dinosaurs were wiped out by an asteroid. That was a pretty fringe theory when I was a kid. People were split. They were like, well, maybe it was a volcano. Maybe it was. I mean, there's all these different ideas, but they ended up actually finding the crater that they believe, the impact zone in the Yucatan. And that basically swayed the consensus opinion over. Now, just because the consensus opinion's behind one thing and the other doesn't mean that it's true. It just means that this is a compelling argument that people are sort of leaning towards. That could change still. And almost everything that we're going to get into is wildly under debates. Like all of these origin stories of the bodies that we're going to be talking about, the celestial bodies in our solar system, they all have really interesting debates. And the stories that were in the textbook when I was in college are different in your textbook in really appreciable ways. And the stories that are going to be there 10, 20 years from now are almost certainly going to be quite different. So, you know, I think science is a fantastic process by which we can interrogate nature and come up with these rational mechanisms for things. But we have to keep that part of our brain open that, you know, we might have a different idea how that works later. And it's a fine line to walk. And that's why we spent so much time last week talking about the motivational structures that underpin these things. Because again, scientists aren't paid in dollars, really. They're paid in something approximating glory, you know, to have their theory be known and hopefully to be correct about it. But this can easily lead to people latching onto things just because it was their idea in the first place. And yeah, so it's quite complicated. Any other thoughts along those lines, guys? Yeah. Yeah. Remind me your name one more time. All right.
Well, that's kind of well, so in that case, if scientists or if people kind of latch on to their ideas because they're theirs, and then like I can see that also happening with like other people latching onto the ideas because there's like substantial like evidence of like this is my scientific um like
This is my work. Yeah. And well, there's a real doozy here because oftentimes, look, like just because you can argue for something being the case doesn't mean that you're right about it, right? There's been numerous, you know, I think that the court system is a great analog for what we do in science in some sense, because you argue based on some evidence that you put out on the table for some angle or another, right? And just because you're super smart and you can win an argument doesn't mean you're right. And we've seen this time and time again in the court system. There's innocent people convicted. There's people sent to their death all of the time. It's really terrible. Now, why is that? It's like, well, they did look guilty, right? They might not have been, but it looks really bad, right? And so I think the same thing can happen in science too, where, and I think you can be sort of blinded to it as a scientist, unfortunately. Like you can find yourself being so enamored with your argumentation on some subconscious level that you might be blinded to things that fly in the face of it. I've heard it said, and I really respect people who, I was recently meeting with this fantastic fusion researcher who's a really interesting character. He's actually an amateur researcher. He basically built this lab in his basement, and he's published in Nature some of his stuff, which is unheard of. You know, he's not part of a university. Nature, by the way, is like the biggest, the most wide-read scientific publication in the world. So this is pretty crazy that he did this. And, you know, one thing he kept coming back to was that he kept, as he was making these discoveries, he was trying to talk himself out of it. He was like, there's no way what I'm saying is true. And all of his experiments were designed to talk him out of actually what he was seeing. Because he didn't want to believe that he had this really far out finding. He thought that, you know, he would just try to understand something about this system and maybe learn from it. He had no intention of publishing it or anything, but he was approaching it from a very pure curiosity-driven space. And ideally, that's what we're doing in the laboratory, is we're trying to really fight against ourselves, right? And sometimes, I wouldn't say like more often than not, but you can definitely get locked into the trap of trying to prove yourself correct as opposed to chalk yourself out of it.
But there's glory in that too, right? Because
Absolutely.
scale science is the unrelenting progression of knowledge to be able to explain what's happening around us, right?
Yeah, absolutely.
At some point, stick a flag in the ground and say, here's an explanation for it. And as long as there's rigor involved in that, then the next person comes up and says, no, this is what I found, this is what's different.
Absolutely. Absolutely. And that's why it's worked so well to this point. It's really a fantastic system. There are situations though where that can break down, and I think it's really easy to be blinded to them, both on the inside and on the outside. Um, it's very you don't really learn this until you start trying to actually do experiments yourself, and you start to realize. I noticed this from a very young age because I was working in labs when I was in college and everything, and you start to notice that oftentimes just the decision about how the experiment is structured can lead to a narrow set of answers, right? And I think a lot of this operates on, that's why I keep pointing to this like substratum of thinking. It's not necessarily that most people are devious about this, right? And that's a really hard thing to separate because it's often really difficult to see whether something, a whole body of knowledge which crumbles was the result of people being devious about the cultivation of the data, or whether it was just laser focus on some end, right? And I think both happen. I think most people aren't sociopaths. They really do believe in the project of science and the accumulation of knowledge and the human project in general. So I think that's a pretty small minority of people that are really just kind of cooking the books, but it happens for sure. A famous example is Gregor Mendel, right? So Mendel was known for doing all of the original work on heredity. He did all of the, you guys probably had to do those really painful Punnett square things back in biology in high school or something. So he kind of set up that method, and he used these little pea plants, you might recall. And it turns out like that his findings were definitely instrumental in understanding heredity, but the actual results that he generated were untenable. When people went back and looked at them and tried to reproduce them in the early 20th century and so forth, they couldn't do it. Now, the things he was reporting weren't super far off, but it was kind of clear that he was in possession of some belief structure about what he was seeing, and that he was designing, in some sense, the collection of that data to support that idea. And I think that that's really what happens a lot more often than not. Generally speaking, it's not cataclysmic because, hey, Mendel had a good idea. He was onto something, and it kind of proved out over time. Alleles are inherited in some sense. They sort separately, but it's a much more complex, nuanced phenomenon than that. When you get into genetics and epigenetics and the modification of DNA by RNA, and it's like it gets really, really nuanced and complex. And he kind of smoothed over a lot of that stuff. Perhaps in his data, he smoothed over it as well. So yeah, I just want us to be aware that there's a human level to this. These are people doing things. They have motivations. We all have motivations. We have reasons for doing the things we do. They're not always childlike motivations, and it's very difficult to separate the adult world of accomplishments and reward structures from what you're doing. And so, yeah, I think this will keep coming up. So this isn't the last time we'll be talking about it. We'll see examples of this time and time again. And I think it will help us understand why some of the biggest ideas in astrophysics and cosmology, if you guys stick around next semester, I mean, some foundational ideas about how the stars work and stuff are imminently in the crosshair. So I think that we will see a massive revolution in the way we think about the way that stars work very soon. Some of the planetary stuff, our own planet's origins, probably will be revolutionized in your lifetimes. So you have to ask the questions when those things happen, why they happen and why we believed the wrong thing for so very long. It's often a very complex, motivational, systematic problem that has nothing to do with the fact that science is garbage or anything like that. It's really not that at all. Yeah. Tammy.
is like technology is always changing, and so we're getting a broader scope of telescopes and like ways that we can actually see things like light emanating from a human or something that we have.
Yeah, that stuff's really cool for sure. Biophotons. I think some of it does lead to revolutions when we can see further and we see more.
So you have to be ready, maybe as a scientist, to be disproven in the future, maybe as technology evolves.
I mean, that would be wonderful if you were, yeah. But oftentimes, new technological advancements are just used to kind of fine-tune our pre-existing knowledge. A great example of that is the story of the origin of the cosmos, which is kind of beyond the scope of the first semester here. We'll talk about it a lot more next semester, but we have this giant origin story for our universe. It's called the Big Bang. Now, I have a friend who works in Silicon Valley. He's one of my oldest friends, or he's one of my more elderly friends. I think he's 65. But he remembers when he was a kid that the universe was thought to be, I think, 3 billion years old. As he grew up, they changed the age to 6 billion. Then it moved to 11 billion. And then it moved to 12 something, which it was when I was a kid. And basically, they keep adding time onto the universe, right? You might think, why are they doing that? Well, it turns out that they're building better and better technologies. They can see further and further. And what do they see when they look with their new telescope? Well, instead of looking back in time, right? We'll talk about this in a minute, but the light takes a really long time to travel here. So when you see the edge of the universe, the edge, quote unquote, it's not like there's a hard wall there, but they're seeing as far as they can. Well, they predicted that they were going to see, baby, let's say, the early embers of the universe, right? But instead, at each turn, they've seen fully formed galaxies. They've seen basically things that, for all intents and purposes, look very much like the things around us. And so they keep pushing the state back, right? And I think that this is something that we can do for hundreds of years sometimes, is we can kind of like fine tune these and move things around and squish our theory around so that we don't have to fundamentally reorient ourselves towards the reality. So sometimes new technology, the new data can be incorporated in a way that it doesn't necessarily lead to a complete revolution in our way of thinking, at least not in any immediate sense. Yeah.
One thing I noticed is that sometimes even an incorrect theory, or you know, at the time it could be correct, it being later disproven could only have happened, and that new discovery would only have happened had the wrong theory had come in place.
Yeah, it's awesome, right?
Science is constantly, everything is, all of our knowledge is built on the knowledge that had to be, discovered.
Yeah. Yeah.
In the article we just read, chapter 1, they mentioned how we currently know more, just a basic, education from elementary school.
Yeah. It's insane.
About science and about the universe.
Yeah, it's unbelievable. I mean, your phone, you can just go on Wikipedia or whatever. Go on, go to the Stax astronomy textbook or go to ChatGPT. The amount of knowledge we have is incredible. The question is how we tie it all together. This is great. Let's start over here. Yeah. Cats. Yeah.
Bouncing off of that, the discussion that we've been having so far kind of like makes me think with the no broad range. You said that astronomy should be studying of bodies that live on the planet, but you mentioned that it's not like sound represents the body or idea and relationships within them. But what got me was that you said they could be real or imaginary. So I think that, like, the imaginary portion is like theories that scientists like kind of like that are intertwined with like the morals of like their work.
Oh yeah, absolutely.
Could you expand on that? Because it's like,
yeah. So at the end of the last class, I kind of left you with this crazy idea that all of the sounds that fly out of your mouth really represent one of two things. One of them being a body, which is something that has architecture, right? We're all familiar with like tables and chairs and water bottles, and it's pretty easy for a child really to distinguish between a body and anything else. And the anything else is really a relationship among bodies or a relationship among relationships. So you can get increasingly nested levels of complex abstraction out of this. That's why humans have, I think, in some sense, mastered the globe as far as our scale is concerned. Maybe bacteria are doing better than us, but we're doing pretty good because we're able to manipulate all of these abstractions in our minds. That's really cool. Problem is, you're right, bodies don't have to exist, right? You can imagine a leprechaun or a unicorn, and astronomers, you know, more next semester we'll be dealing with this because we'll be, this semester we're mostly just looking at things that are in our solar system. We can see them really well. There's nothing in the way of imaginary bodies in our solar system that I can see. However, when we start going really far and we have very little evidence, in other words, we have very little light to examine a lot of the things that we see far away. And oftentimes we start to imagine what those things we see could be. Now, whether they're actually there or not, whether they're imaginary bodies or real bodies, becomes a really interesting piece of the puzzle. And so, yeah, this fundamental swapping out of imaginary bodies for real bodies, of ideas for bodies, that's one that's actually more common in fundamental physics. A number of you mentioned that you had interests in quantum mechanics, things like that. We'll be dealing with that as it comes up. But there's very much cases where mathematical relationships are treated as if they're physical bodies doing things. My favorite one, and by the way, it could be an absolutely valid mathematical treatment. So I could say something like, the force caused this to, like I applied a force. Again, I shouldn't say I applied, but like the force caused this. The force of my hand caused this bottle to move across the table. Well, it's like the force is an idea, first of all. It's a concept for the amount of effort that's being placed in the collision between my hand and this thing, right? But you have to be really careful because forces don't do anything. They're not in physics anyways. They're not actually physical objects capable of doing anything. And so there's this strange reification that happens. And when you get really deep into the mathematics, sometimes you can get to the point where all you're doing is moving abstractions around and they don't actually terminate in anything physical at the end of the day. And that, I think, has resulted in a tremendous proliferation of irrationality inside of the really deep fundamental mathematical physics. And I'll substantiate all that in time when we get to some examples that make sense. So we'll be circling back on all of these. I really want to spend like the first week or two here making sure all these basic concepts are laid out before we start applying them to real situations, so that we're at least on the same page about what's exciting here, other than what's just printed in your textbook. In the back, yeah.
I just was thinking about earlier we were talking about, I didn't know the thing about like those reverse repeat seeing farther. I didn't know that, and I just thought that was interesting. And I just like wanted to like pose that question of like, do you think we'll ever like see that wall? You know what I mean? Or do you think like as the technology continues to expand, we'll just like continually see more and more and more, and it's infinite, that the age of the universe will just keep getting bigger. It's like a vicious cycle. It's won't stop, I guess.
Yeah, I don't know. Well, there's two possibilities, I guess. These are cosmic. These are more. We'll be hitting all this stuff really tight next semester if you hang around. There's two real possibilities, right? The universe has a beginning and an end, and it has physically a begin. It has physical boundaries to it. Those are sort of two different questions in my mind. And I think that we can pursue logical answers for both of them. Obviously, the popular idea right now, although I would say it's been popular since long before science, is that the universe has a beginning to it. It started one day, and it will end one day. I think those are pre-existing metaphysical assumptions that have been sort of mapped onto what we see in the sky personally. And I'll compare the cases for both next semester in more depth. But if I was a betting man, I would say that the next telescope we see will extend the age of the universe even further. And so I know a number of theoreticians working at some pretty big, fancy universities who are already anticipating that and trying to rectify, and in some sense, trying to save their Big Bang Theory for the next generation of telescopes. And I imagine they could keep doing that for several hundred years, honestly. I think that this is the last thing, I don't want to get too deep into cosmology because we have to get onto the solar system in this course. I would say that, let me ask you this, I always love asking people this. How many of you are comfortable with the universe having no birthday and no death day. It's just always been here. It will always be here. I'm not judging you. I'm just curious. And how many of you are deeply uncomfortable with the universe having no beginning or end? Okay. Yeah. That's interesting. It usually tilts more towards people being uncomfortable with the universe not having a birthday. So I don't know. I think that prior to the 20th century, actually, most people thought the universe. Most people, sorry, most let's say intellectuals, whatever you would have called scientists back in the 1800s, they didn't call themselves scientists. They probably would have embraced a more eternal universe. It's become very popular in the 20th century for largely on the back of this Big Bang thing, which we're not dealing with until next semester again, to lean into this beginning and end situation. In some sense, I just think those are metaphysical dispositions that are very difficult to sort out. The Big Bang theory is actually built on 2, maybe 3 pieces of evidence, and the main 2 are most people recite them without really understanding them, and so we'll look at those in depth next semester and let you guys make up your own mind about it. But again, it's also totally possible that when light travels for 14 billion light years, I mean, light is traveling really fast, right? And we'll have to get into what light is and all of that eventually. But you know, it's traveling at something like 300 kilometers per second. Okay, so we're talking about gajillions of kilometers from where this light is originating that we see with our most distant telescopes. And what happens to the light as it travels that far? No one knows. There's no way to set up an experiment on Earth where you understand what it's like. I mean, even if you just reflected light off of a mirror, you'd still need 13 billion years worth of time to actually make any conclusions about that. It's very, very tricky experimental situation to assess. I personally suppose that as light travels across such a vast distances, it's interacting with so much that maybe there will be an ultimate limit, but for which we can actually assess those light signals, despite how great our telescopes get. Which is weird, because if that happens, then people will then like the people who are metaphysically predisposed to there being an origin of the universe will probably say that, oh, well, that's the edge of the universe and that's it. But I think a reasonable argument could be made that that's just the limits of light's travel path in some sense. It's a very difficult question to answer. Yeah.
One of my favorite examples of sort of imaginary bodies
Yeah.
is black holes.
Absolutely.
Finally actually observed one a few years ago.
It's well,
It was very blurry.
That's pretty. It's quite a data hacking job too.
Like visual for what a black hole looks like.
Yeah.
Was made with just math for the movie Interstellar.
That's right. Yeah.
It was all just math.
Yeah.
That theoretically that's what it would look like.
That's right.
And we just accepted that that's what it looked
Yeah.
like. And then our little observation, this little blurry blob.
Yeah. What if I told you that picture that you saw in all the headlines came from 8 voxels worth of information, actually? So they screened out gajillions of voxels. Voxels are just 3D pixels worth of information to produce that map. I mean, I don't want to get into it right now because I want to go through that paper with the luxury of detail it deserves. It's pretty bad science, so I'll be honest with you. It's really bad science. But we'll go through it next semester if you guys are interested in that kind of thing. We'll give black holes their due diligence. But I agree. That's a great example of an imaginary object. Yeah. Remind me your name. What is it? Kenzie. All right.
Before, I was just curious, how do we know, like we say there's a beginning, if we don't know what it is? Like, is that just because of the Big Bang Theory?
Yeah, I mean, yeah, I don't think that we should get too I would love to talk to you about this before or after class, but we do have to focus a bit on what's nearest to us in this first semester. If you want to hang around next semester, we'll be dealing with all of this stuff: Big Bang, black holes, white dwarfs, all the fancy, crazy stuff that you hear about. That's pretty much all next semester. But yes, that age is deduced. Again, it's deduced on 2 pieces of evidence. One has to do with the way that light redshifts as it travels across the cosmos, and largely gives us the the distance, which we can then multiply by the speed of light to get kind of how far away it is, and how long it took. And so, yeah, it's a deduction.
I think, well, you're right when you say that it's mostly based off of a predisposition of us believing that there's a beginning. We assume there must be a beginning and an end to the universe because everything we observe
That's right, yeah.
has a beginning and an end.
That's right.
Even stars, unfathomably old
Right.
to us, we know they have a birth and a death.
Yeah, and we all do, right?
And so it's hard for us to imagine something like the universe that has changed as much as it has, being truly eternal, having always existed and will always exist. It's a comforting thought to some degree, but we, in our heads, just because we know everything dies, we assume the universe
Yeah,
was born.
yeah. I think that, I mean, yeah, we'll get into it with the luxury of detail it deserves next semester, but I think you're absolutely onto something at least. That seems to be certainly true. I think it's I think we're always fighting against trying to map our experience onto everything's experience. I mean, the universe is an insane place. Let's not like mince any words about it. It's pretty wild that there's something here at all. It's even more wild that all these atoms have organized themselves into beings that are sitting here in a classroom in Southern Oregon. Like, it's something very profound and strange about this place. But yeah, whether there's this, miraculous creation event or whether it's been here for all of eternity, they're both pretty amazing and hard to stick inside of your head. Like, it's very hard to behold this entire place in a rational sense. It defies comprehension, I think, from both angles. Both tend to really stress and stretch people's minds. Yeah. Nolan, hey.
I think it's just weird, kind of awkward. It, I'm not there. It's just the thought of it, of how we know getting or not, which is very religious, in a way.
Well, the religions certainly tried to deal with it for most of history, yeah. I mean, because ultimately people want answers, people want to know, what am I doing here? How did this get here? Why is this place here? Like, those are reasonable questions. I think most children ask those questions. It's only been recently, I think, though, that the sort of intellectual class, the philosophers, the scientists have been tasked with answering that question. And that's what's very interesting, and this gets back to like whether science is capable of answering everything. Can science answer the question of why there's a universe instead of no universe? I don't know that it can. Yeah, it's tricky. And so yeah, religion. We'll talk about all these things as we move on. But religion, in some sense, still remains quite popular throughout the world, and it's even popular with many scientists, many very physically oriented people. I think they see it as fulfilling sort of a different role, really. Again, that gets into the question of like, can science really deal with everything? Some of the brightest minds that are out there think no, it can't, and I prefer this other framework for beholding certain problems in humanity. It's more productive to me to look at it through this religious lens or the spiritual lens or some other lens besides just cold hard atoms doing things. That doesn't, I don't see them really being at war with each other personally. I see them as just being two different ways to look at the same picture. So we'll talk more about that. All right. Anybody want to say something who didn't get to? Otherwise, we'll just keep moving through our story here. It was really good to meet all you guys in your videos too, by the way. Everybody's doing really cool stuff. You guys seem to oh, that reminds me. A lot of you mentioned that you do music or some sort of craft or something. There is an optional extra credit project in this class. So, and it's due at the same time as the final project. If you have some talent, skill, craft that you explore creatively, you can put that to use and you can kind of invent your own project. I've had students do everything from books of poetry, of course, pin it to what we're doing in the class to some extent. And it's a huge class in terms of what we're talking about, which is almost everything. So you can probably find a way to pin it. I've had people do short films. I've had a lot of paintings. time-lapse photography, really anything that suits you. And it's worth quite a bit of points, actually. So if your grade is flagging you in any way, I highly suggest that you start thinking about that. And it's kind of an effort-based thing. So how much effort you put into it will reflect how many points you get. And I'll just sort of decide that tyrannically. Any questions about that? All right. All right, let's keep going with all of this. Gosh, you guys wanted to know about all of these interesting questions. I had a lot of people who want to know. They were hoping science could answer questions about consciousness, life after death, life on other planets. We'll get into a number of these topics, I think. Maybe we can't get too much into consciousness, although it seems like we're already going there. Okay, so where did we leave off here? We talked a little bit about what astronomy was last time. We talked about really chaos versus order and this attempt to map patterns of what we see in the sky and construct stories that explain what happened. And people have been at that project for so much longer than they've been doing this sort of methodological approach to trying on these rational explanations for what they're seeing. It's often been more symbolic in nature. What else did we talk about? We talked about bodies. That's where we left off, was with bodies. So let's talk about exactly what science is at this point, because we've been dancing around it a bit. I think I'll actually read you. There's a book that I have here, which is a really good book. I'll probably be reading some passages from it as we go ahead. It's actually written on the basis of indigenous astronomy, which is wild. And it's actually, this foreword's written by the Native American chair at Harvard. I guess he was, he's not anymore. His name's Leroy Little Bear. But I think he has a kind of a good, I'm gonna just read the foreword to this book, a little bit of it, because I think it'll kind of stimulate some discussion here. So he says, science has been and can be defined many different ways depending on who's doing the defining. But one thing is certain is that science is culturally relative. All right, we'll get back to that. In other words, what is considered science is dependent on the cultural worldview paradigm of the definer. Immanuel Kant, who divided knowledge into appearances, reality, and theory, suggests that the appearances of the world are deeply conditioned by the human sensory and intellectual apparatus. Other beings no doubt experience the same world in radically different ways. Scientific facts, the appearances themselves, are as much a product of the observer's human nature as they are of an underlying reality. And so we see the world through a particularly human goggles, which I think is true. Albert Einstein said that the business of science is reality. I agree, but the reality brought about by modern science is largely based on Western paradigms. Western paradigmatic views of science are largely about measurement using Western mathematics, but nature is not mathematical. Mathematics is superimposed on nature like a grid and then examined from that framework. It is like the land survey system, a grid framework of townships, sections, and acres superimposed on the land. These units, in turn, are used as a basis for dealing with the land, but they are not part of the land itself. Einstein was so enthralled with the mathematization of nature that he once observed, quote, "How can it be that mathematics, being a product of human thought which is independent of experience, is so admirably appropriate to the objects of reality?" All right. So what is he on about here? In some sense, I think that he is recapitulating what we've talked on a bit at the beginning of this, which is that we do have these human motivational structures, and we have a way of coming at a problem from the get-go. This is, I think, why the Big Bang came up so early on here, is that there is a disposition we have towards addressing some reality. And you can see it change over the course of the drift of different cultures, right? So he talks about the mathematization of science, and I think that's quite interesting. In some sense, we have here two different models of the solar system. This is the pre-Copernican system, where you have the Earth at the center of the solar system. And this is the post-Copernican system, the one that we have today, where we have the sun, all little planets going around it, and these nice little, almost circular orbits, not quite. Now, what's really interesting, though, that I love to point out, is that both of these models are extraordinarily predictive mathematically. In other words, the Greek, actually, the Ptolemaic Egyptians, which were really Greeks, really developed, and the Arabians helped to some extent, develop the mathematics of this system to the extent that they could predict the location of bodies using these mathematical equations with extraordinary degree of accuracy. The reason I'm pointing this out is because you can have really, really accurate mathematics and be completely wrong about what you're talking about. And that's kind of mind-blowing if you think about it. So you can, oftentimes if I ask people, what are the things that science should be doing? And it's like often like, well, it should make really accurate predictions. It should take really accurate measurements. It should provide, and then the last piece is kind of like it should provide a theory for how things work, right? It should provide a picture, which is in some sense an explanation for how things work. So when we were talking about can science describe everything, and I said, I think there's a very big difference between description and explanation. The Ptolemaic solar system was highly descriptive and very accurate, actually. But it was the wrong explanation at the end of the day. And I think that as we move into the modern future with all of this data rushing in from all these extraordinarily high-tech devices and measurement apparatuses, we're going to be faced with this kind of a problem more in the future, where this kind of rectification, where we have to take all of these extraordinarily predictive understandings, these patterns that we've sussed out. Maybe we've put incredible mathematical theories to them. Theories like quantum mechanics, theories like electrodynamics and electromagnetism, these really, really highly precise and well-vetted mathematical theories. But we don't totally understand what's happening still. And that's the future of a lot of the topics that we're going to be looking at, particularly when it comes to explaining where these objects come from, where do solar systems come from. We got a lot of data. We can make we understand in some sense the mathematical patterns, the physical laws that describe their motions and behaviors, but there's a huge possibility that we're seeing things completely wrong at the same time. I think that's really exciting, actually. I don't think it should be unnerving at all. But I think it's really, really important to understand that there's a difference between descriptive accuracy, predictive accuracy, which kind of goes hand in hand, and then the actual explanatory power of the theory that you're generating. So, yeah, you can be completely wrong and the math works just fine. That's quite interesting. So, I think we have to just, this again comes back to this idea of taking some humility with respect to the certainty that we arrive at, just because your understanding of the system is mapped really nicely onto the patterns that you see does not necessarily close the door on the fact that you're missing some fundamental reframing of the problem that could change everything ultimately, right? Let's say, to take this Big Bang thing a little bit further, maybe in the future, the metaphysical basis, the metaphysical predisposition of the culture shifts in such a way that eternity becomes more of a, let's say, grounding paradigm. It seems to appeal to people's intuitions better. I think it would be quite equally possible to map theories onto why we see these red shifts, why we see this microwave background. We could probably come up with explanations that are congruent mathematically, but have a totally different endpoint as a result of them. And so that's really, really quite an interesting feature that I want you guys to pay attention to as you go out into the world. The science is kind of divided really neatly into observations and pattern making, but then there's also this theoretical layer that's sort of pasted over it, and that's the part that you have to kind of keep a little bit of valence about. Well, this almost certainly will change, and if it doesn't, it will probably be updated to some extent. But oftentimes, the theoretical overlay gets completely rewritten, sometimes quite quickly, actually. And we'll see some examples of that. Thoughts, questions? Yeah.
Well, I guess to me it seems like with the math, like with this whole example, like if the math lines up and you're like, and it still can continue to line up, like you're talking about, like it feels like the science. It's not like it's wrong. You're just missing something.
Yeah.
Like I feel like you're not wrong. I mean, you're not right necessarily either, but I feel like it's like I guess I would just kind of. I don't know if you do it exactly like I wouldn't say that you would be wrong in that sense. Like, you're just not equipped to deal with all of it.
Yeah. Absolutely. And just having another little piece of the puzzle, right? Just having a little bit of a different way of looking at it. Now, by the way, I didn't even mention some of the metaphysical assumptions that went into this. I mean, it was a strong belief for most of human history in terms of the people that were looking at the stars trying to come up with explanations, that the circle was the most perfect geometric object possible. And a lot of the reason that they ended up with this model is because they were predisposed to believing that the celestial bodies, well, they were spherical, and honestly, everybody believed that they should be moving in circular patterns. That made the most sense. It's the most perfect object. And it was obviously a deeply deistic society. They couldn't believe the mind of God would do something less than perfect. And so it took kind of a couple of weirdos to come along and say, hey, what if they aren't circular orbits? What if they're like a little bit, squished? What if they're a little bit elliptical? And by kind of trying on that idea for the first time, they were able to come up with this model. Now, the reason this model was ultimately accepted was in some sense technological. Some guy decided to basically take a telescope that they were using for, the Dutch were actually building these for maritime travel, right? For, like pirates or whatever, like that. And he decided to look at the sky. That was Galileo. He decided to actually look, and he actually saw the phases of Venus, for instance, which is kind of like the moon. It has phases as it goes around the sun. He also saw the moons orbiting Jupiter for the first time. And so he started thinking, wait a second, like there's little things going around this one body. Oh no, what if our things are going, he kind of put it together in that sense. Copernicus had already put forward his idea here. And so everybody kind of jumped on the bandwagon. And I think in some sense it was by being able to interpret those new technological observations and integrate them into something that made a little more sense. Yeah.
Sorry, my name is Max.
Gotcha.
Could you argue in like a weird way that yeah, they were obviously very wrong, but like it kind of worked for them?
Yeah, absolutely. That's what's so crazy about this. And it's like why I think it's really important not to confuse science and technology. You can take those predictive laws and you can do a lot with them. This case is a little bit odd, but electrodynamics and electromagnetism are a great example. Like we're obviously really good at describing how currents in circuits behave. We can build, computers, cell phones, cameras, right? We can manipulate these laws in such a way that we can build incredible, bordering on magical devices, right? Certainly if I would have taken this to somebody, 500 years ago living here in Oregon and just like started showing them stuff, like they would have thought I was like a wizard or something, right? It's just unimaginable. But the closer you look at things like electrodynamics and electromagnetism, the more you start to realize that our picture of what's actually happening, in other words, what are the atoms actually doing to each other? You might say something like, well, they're like passing electrons along to each other. But then you might ask, well, what exactly is an electron and how does it do that stuff? What is charge exactly? What does it mean to be charged? Well, it's an oppositional force. No. Like, what is the atom doing to the next atom in order to charge it? What are the physical interactions? And those are complete blank spots, actually. That's what I'm trying to get at, is that the work of your generation, of the next generation, is largely going to be trying to make sense of the things that we thought we kind of understood. But in some sense, we passed off these descriptions as if they were explanations because they were so technologically prolific. They're so good. Like you don't actually have to understand things fundamentally in order to make gizmos that work. So, that's kind of one of the reasons that I'm trying to center this divide between technology, science, but also when it comes to science, there's no the science, right? There's just what we see, how it maps onto some sort of patterns, and then there's people who come up with ideas about what those patterns mean. And there's a real free-for-all about that. So that's a theoretical landscape that's honestly, as far as I can tell, eternally subject to revision.
One of my favorite examples about how easy it is for the human brain to recognize patterns where there are none are optical illusions.
Yeah.
Because our brains are made, at least we believe are made, we don't want patterns. We want things to line up and make sense and not just have no.
Yeah, order from chaos, absolutely.
Yeah, when some lines on a piece of paper, our eyes see a cube.
Yeah, or have you ever seen like faces on trees before? That kind of thing on stumps, called pareidolia, I think.
I talked about this in one of the responses, but it's like humans are like naturally wired to be afraid to be unknown.
Yeah, that's what this project's about. That's what science is really about. It's like honestly, it's noble. And I think a lot of what we do is trying to come up with some structure for an otherwise chaotic and frightening environment. And a lot of this happens like below the level of consciousness, right? Like there's an order that's quite comforting to us in everything we do. Like you guys all know when you come in to sit in the seats where you sit. Like nobody's just coming and sitting on the stage. Like there's all these like little rules that everybody just follows, and you might think like, well, that's really oppressive that we have to do all these rules. And it's like, no, it makes everything easier, right? We can actually get on with the project here of having this discussion in this organized fashion. Like all these little orders that we've put into place, they're quite functional and useful to us. Perhaps primarily because they remove a lot of the anxiety of existence from an otherwise maddening world where God knows why anything happens. It's very hard to deal with. So yeah, it has a lot of promise. It definitely has a lot of promise as a method. So I'll get to you in 1 second. I would just add that in addition to science being about, my whole point here is that in addition to science certainly being about this increasing degree of accumulation of knowledge about, and I'm talking about empirical knowledge, like experiments, collecting data about the stars and the motion of the planets, that's a huge part of it. Assigning patterns to it, we'll call them physical laws, is another big part of it. But there's another part of it which is assigning mechanistic explanations for what's happening. And I think that's the part that doesn't get enough attention, especially in our present academic structures. It's very easy to make your way all the way through to a PhD without totally answering those kinds of questions about what's actually happening here, right? You can get by with something like this for a really long time, especially if it's technologically feasible. So there's a very complex endeavor, science. It's not this simple monolithic thing that is completely without a human element. And I think that's really exciting, personally. But it does mean that we have to have a little bit of humility about the theoretical layer that we paste on top of it. All right, let's keep rolling. So I want to introduce a couple of terms here. One of the things that I think probably your textbook terribly confuses, but you guys can tell me if I'm wrong about this, is the difference between a theory and a hypothesis. This was kind of maddening for me as I was coming up and learning to do science. It's often said in the textbooks that a theory is something like a hypothesis which has been proven. Now, I don't like that for a couple of reasons. First of all, because the word proof is a mathematical concept. It really just means that you have followed the logic of your assumptions to their eventual conclusion, which is cool, which is fine. But in the sense of like a court case or a trial, it's difficult to ever actually prove anything with any degree of absolute certainty. It still has a theoretical valence to it. So I like to think about these things a little bit differently, and I like this is actually the philosopher René Descartes. This is his definition of a hypothesis. For Descartes, a hypothesis was actually something that you thought could be the sort of linchpin in an explanation that would provide that explanation to be true. So, for instance, with our previous gentleman, Copernicus, if the planets were to actually orbit in these elliptical orbits, then it would make a lot of sense why what we see with these brand new inventions, the telescopes, look the way that they look. It would explain it. It's still a hypothesis, right? We don't know if it's true or not, and increasingly, now that we've been able to send spacecraft out and all of this, it seems to be really the case, actually. But they didn't know that in that time. So Descartes said essentially that a hypothesis is a supposition. So it's like, I suppose this could be. Supposition not necessarily supplied as definitely true, but if it was true, it would be sufficient to make sense of the phenomenon that you're observing. And I like that a lot. Because in some sense, like we talked about at the beginning of class today, your job as a scientist should really be to talk yourself out of that hypothesis, right? You should really be like, well, this would explain it, but is there any other way I could explain it? Is there something wrong with this explanation? Is there a reason why it couldn't be the case that the planets are orbiting the sun the way that I'm thinking they might be? That sort of culture of doubt is really, really healthy in science, and it, in some circles has evaporated. So I like to center on that. So that makes the theory really just the explanation. That's the final abstraction layer that's mapped on top of the phenomenon, where you're actually getting into what causes what you think causes. That's the mechanistic side that I like to overlay with all of this very detailed, unassailable empirical evidence that a mass is. So we can thank Descartes for that one. And again, testing these things is very important. There's ways to actually talk yourself out of your ideas. There's ways to do that in a laboratory, but again, you're still susceptible to how you're designing those experiments and whether you're actually open to the idea that you're wrong. So things get a little bit tricky with that, as we've discussed at the beginning of class. All right, so this brings us kind of full circle back to mathematics. And I think I kind of made my point with respect to the Copernican versus the Ptolemaic systems, right? Extremely predictive, accurate mathematics, but the final layer of tying all the pieces together turns out to be quite different than anyone expected. You know, it's often said, I think actually your textbook even mentions this, that mathematics is sort of the language of science. And I really wrestled with that idea for a long time, because I started thinking about it in a really nerdy way, and I started thinking about, can you actually make a sentence with mathematics? And what part of speech would these things be if it were the case, right? And what I came down on is that math is almost exclusively quantitative adverbs, and you can't actually construct a sentence out of quantitative adverbs. At the end of the day, I can write an equation on the board, but I still need to qualify each one of the variables in that equation. I need to say, this F, if I write, say, F equals ma on the board, I need to tell you what the heck a force is, I need to tell you what mass means, and I need to tell you what acceleration means. These are extraordinarily complex abstractions that are going to require whole conversations. And it turns out that this really is the case with all math. It actually all requires qualifications, which is natural language to describe what's happening inside of these relationships. And so I think that we're sort of doing a disservice to ourselves by treating math as if it's a language on its own. Because if we treat it as if it's a language, then it seems like the math is sufficient to explain phenomena, which, by way of the Copernican Ptolemaic example, clearly isn't the case. The Ptolemaics had fantastic math to describe the motions of the bodies, but at the end of the day, it was that natural language reckoning, it was that mapping of the theoretical landscape onto the top of it, interpreting the maths, that actually took it to the next level, where we have the solar system that we're going to be looking at throughout the rest of this course. Make sense? Questions? Concerns? Yeah.
So I actually watched that video.
Oh yeah, I wanted to plug this video. So
Those guys are meant to be like aliens, right?
yeah, so I put this video in your guys in Moodle for you guys. I hope you check it out. It was the last movie that my wife and I made with these alien puppets. We started off kind of our media career trying to do these. It was a tremendous amount of work, and they weren't getting watched as much, so we decided to just do podcasts instead, which are doing way better. But the whole argument here was these alien scientists show up on Earth, and they're trying to make sense of why in the world the humans think math is a language.
I was going to say though, do you think if we were to meet another like sentient life form that understood math on the same level, if we'd be able to compare the two, or if they'd be completely just like not, you can't talk to each other?
Yeah, I could see what you're saying. Like, is there a quantitative commonality? I think so. I mean, the symbolic structure would probably be different. There is something really funny though about math, which is that it's actually in some sense inherently quantized into discrete values, right? So, you know, you count in terms of integers, 1, 2, 3, 4, right? However, there's a great deal of the pattern matching in nature which doesn't fit nicely onto these nice little quantities, right? You know this maybe as the irrational number. I guess pi is a great example, right? The ratio of the diameter of a circle to its circumference. It's just an unending sea of digits, right? It doesn't divide neatly. And much of nature is like this. We have the exponential function. There's all of these different continuum dynamics that play out that don't map neatly onto our idea of quantity. And so I think quantity in terms of discrete numbers is like a really, really productive way for us to develop technology and understand certain phenomena, but it has its limits too. I think that, what's a good example of this? Well, it's like, here's a good question. Like, if I asked you to go outside and count how many apples were on a given tree, and let's say it was like early spring, well, you might at some point find yourself, spend all afternoon doing this, and at some point you might come to me and be like, well, that one, does that count as an apple yet? It's still sort of flowering. And I'm like, I don't know. I mean, does it, right? Like there's this strange continuum by which we impose this discreteness on it. And actually, as we get deeper into some of the mysteries of fundamental physics and quantum mechanics and gravity and things like this, which we will touch on eventually, we'll start to see the breakdown of the way that we measure things versus the reality that's underneath them and how it really tests the limit of our ability to handle them in terms of quantities. So yeah, Andrew.
Two things. First of all, I think it's fair to say that humanity has historically had a very difficult time comprehending spectrums.
Yeah, absolutely.
Secondly, I remember watching this video when it came out.
You're kidding me.
No idea that this was.
That's unbelievable. It only has a couple of thousand views. That's amazing. Yeah, wow. That's really fun. Yeah, we had a lot of fun with that. When we started I've told you guys, and I post some of these that are relevant to the course. We now do a podcast where we talk to different scientists about, kind of their challenges to advancing some ideas, that might be, hopefully, some of the best ones hopefully will become the theories that we view the world through later. But it's funny, when we first started doing it, we were using the alien puppets because we were really scared, if this project does really well, then we'll have, millions of viewers, and we don't want people coming to talk to us in airports. But it didn't work out because it's very painful to puppet for 3 hours during a long-form interview with a scientist. And that's really funny that you saw that then. Okay, any more thoughts or concerns? Math, science, yeah.
Some degree, I think math is quite prone to giving us an explanation for something that's not very accurate, just because it can be used to describe almost anything we want, whether or not that exists. Like we can produce a perfectly accurate mathematical prediction for something that works within a very finite bound.
Yes.
And applied to reality, we operate outside of those boundaries.
Yes, absolutely. And well, a lot of this is going to come into play next semester, so I really hope that you'll stay in. Mainly because, like I said, this semester we're going to be looking at the solar system. It's very close, relatively speaking, to the kind of conclusions that are being drawn about the galaxy as a whole, about things beyond the galaxy, where you're actually, again, you're trying to extend some knowledge space that you have from your laboratories on Earth, from the way you understand light behaving on Earth, to these vast distances, right? And you have very little data, and you're trying to fit that in. And I think there is unfortunate, I do think it's a bit unfortunate, but, and we can trace this back as we get there, this desire to universalize your understanding of nature. So you see something in some narrow confines, you can describe it really well in a laboratory. Maybe like the way that light, the way that light is emitted from a heated body, for instance. And then all of a sudden you say, wow, I think this might apply to all of light everywhere. And you move on. And these things get kind of wrapped into the burrito of the canon that the next generation learns, and they just sort of accept these laws as being universal. But there's increasing doubt about a number of these universalized laws, particularly laws that were universalized back in the 19th century, the 18th century. Should we have done that? Does it make sense? Why doesn't the galaxy rotate the way that we thought that it would based on this universal law? There's real questions about whether those sort of generalizations should have been made. So yeah, the concept of limits, to mapping is really important, right? You got to always be careful that when you start mapping phenomena, just like when you're mapping like this room, or you're mapping like a territory at all, that you don't start studying the map instead of studying the actual territory itself. And that's a huge crisis that emerges in all sorts of different disciplines. And of course, we're subject to that same danger, perhaps. Yeah.
Do you think that that leads to kind of like the doubt of science when people do start to doubt science in general? Because when I was young, I'm a little bit older, and we were taught about planets and how this is how they were definitively. You're taught like these things, and then you grow up and you're like, wait, Pluto, what happened? And like, what's going on? And you learn all these new things. And so maybe from the beginning, it never should have been told to us or taught to us as such a thing that's not fluid, like.
Yeah, well, that's what I'm in some sense, I think a huge basis of the reason that I'm motivated to even be here and do this, and be here with you and do this, is because I think that that's been a terrible disservice. Because for me, what's really exciting is how much of, if I can go back to this old slide, like I think there's a lot of this still to be done, right? And so if we just teach things as being this certainty that's based onto these physical laws or whatever, I think we're missing a lot of the fun that's left to be done. The mysteries actually are really where it's at. And if we look at science as this really, really successful project that's actually been able to like cumulatively iterate and come closer and closer to understanding how things work, without being completely captured by the idea that all of those conclusions are completely certain and done, I mean, that's a tightrope to walk, though. Truly, particularly as people, make careers of it and find themselves really committed to their ideas, it becomes very tricky. So, yeah, it's unfortunate. I mean, I get really bummed out when people start doubting science as a whole, right? Now, there's bad science, there's good science. Science involves all these things, observations, testing, but also theories, right? At the end of the day, you're usually just hearing the theories in the textbook. Maybe you're doing some experimental stuff as well, but for the most part, you're learning theories. And so if that gets wrapped into this certainty thing, then it seems like there's not a lot of work left to be done, which is, I think, very, very far from true. So it's very tricky. I find that to be kind of sad and disturbing too. Because the alternative is actually a lot more terrifying if you think about it. I mean, what's the alternative to rational explanations for a phenomenon? It's like, well, what anybody says goes. Basically, whoever has the biggest microphone gets to decide how things go, right? And we've been through the Dark Ages, right? Where there's just this kind of monolithic religious institution that's telling us how things work. And they're going to write about it in a language you can't even understand, and shut up and, pay your dues, basically. And so that's kind of terrifying. That's really the alternative. So, yeah, we might be wrong. In fact, we might, the whole project, in some sense, the way I'm looking at it, is based on being incrementally wrong and readjusting and reassessing and having revolutions in the way we think about stuff. But that's the project. That's the cool part about it, right? It's not that, we've decided everything once and for all.
Excited as a child about science if I knew that there was a soul opening world.
Yeah, me too. Absolutely. Yeah, me too. So that's what, and we're going to look at what's really cool about this course too. And, like I said, we're going to spend a couple of weeks just making sure we understand these basics. But when we start looking at the stories of each of the bodies, we're going to start, we're saving the sun for next semester, but we're going to start with the closest body, which is Mercury. And we're going to start talking about the stories, the theories. First of all, what do people see about Mercury? What do we know about it? What's obvious? What's, in question about it? And then what kind of stories have people tried to rationalize about where this thing came from and how it happened? And there's a huge, huge expanse of people arguing about the nitty-gritties there. There's some that are completely radical ideas. There's some that are sort of clustered in some conservative sense around one another, which are generally ones that have made it into the textbook. But yeah, there's a huge conversation, and it's really, really fertile and incredible. And just in my own lifetime, even those stories that are sort of conservative and consensus stories have drifted in a certain way. I like to think of it as like a paradigm drift a little bit, right? Where people, this might make a little more sense. Let's go that direction. What's really awesome about your guys' textbook is that it's all updated online. I've been in the middle of referencing parts of it when they actually update in real time and include new pieces of information. That's really awesome. So that's never been possible before. When I was a kid or when I was in college, textbooks are probably 10 years behind the times with any of this stuff. So in some sense, maybe the fact that we inherited that way of understanding things was a limitation of the way in which information was distributed back in the days of hard print text and so forth. You have a question? No, sorry. Yeah, Dante.
I remember when I learned that the sun isn't yellow but white.
It does appear a little yellow.
No, we call it a yellow. It's a yellow dwarf. Okay. It looks yellow in the sky. I mean, it's the yellow light will reach you, so it's a yellow dwarf, but it actually produces all the colors of light.
Well, next semester, man, we'll deal with the sun. It's an amazing situation, and the way we're understanding it has changed. It's under some interesting revisions at the moment. All right, so mathematics, it's these quantitative if-then statements. I think another part of this, which you were bringing, remind me your name? Corey was bringing up, was that in some sense, it depends largely, I'm not sure if this is quite where you're hinting at, but part of where you were going with this is that it depends largely on the assumptions that you bring into the table, right? So quantitative logic, like, do you guys know what logic is? What is logic? Anybody have a good definition for it? I guess I already wrote it on the board, but it's basically if-then statements. It's kind of like coding, like, if this is true, then this is true, right? And you sort of can follow these, and there's a whole art form built on this. And math does this with quantities really well. You basically follow these operations, which, if you follow them, you will get to a logical conclusion. But it does depend, in some sense, on the assumptions that go into it, right? If you make this really nice equation to describe how light behaves from a heated body, and your assumption at the beginning is that that's a universalized phenomenon, that applies to all of light everywhere, regardless of what the body is that's heated, whether it's a gas, whether it's a solid, then you might be tempted to find an explanation for it being the case regardless of what you observe, right? You might be able to talk yourself into, well, I don't see it in these kinds of bodies, but under the right conditions, maybe it could be seen, and therefore, well, let's just stick with this universalization thing. So the assumptions are kind of everything when it comes to logic, and that's again the human level of this. It's like on the first day I asked you guys, we were talking a little bit about AI and chats and stuff like that, and they're really good at processing the assumptions that they're given and giving you logical outputs. They can go into the whole body of Wikipedia and knowledge bases and all of this and string together what is based on what's understood. But they're not really going to be capable of going back and reconsidering, like, wait a second, is this assumption that's being made here, is that actually a reasonable assumption? Does that make sense in all situations? I don't think so. So that's a human element that we have to really map our creativity onto. We have to really apply our creativity to. Yeah. Yep.
It makes me think like physics, remove air resistance, or like remove this.
Yeah, yes. You're like, but that's important.
It makes it easier for me.
Yeah. Yeah. It does, and it becomes easier to handle in those circumstances. And there's parameters often that'll be introduced, in mathematical equations to deal with those. Like, well, we just put this little factor here, and it works, right? Again, technologically highly productive in most cases. But then in terms of why do we put this parameter here? What is it actually attenuating in the physical space? That often doesn't get the airplay that it deserves. So we'll see many examples of this as we keep rolling. Yeah.
And I was reminded of this because of the chart you showed with the way I think we saw the revolutions. What exactly defines a planet? Because I know that we used to have different definitions in the past, and it used to be like there was 9 and then 14 or like 20 planets or whatever.
Uh-oh. Sorry. Yeah, I actually have a slide come up, but let's just deal with it right now. So the word planet actually comes from the Greek word for wanderer. So they were the stars that didn't stay in the same place every night, right? So for the Greeks, actually, they kind of inherited this from the Mesopotamians, who were really the first people making star catalogs in the West. And they noticed very quickly that there's certain stars that are actually traveling across the night sky from night to night. So they just give the word planet to anything that does that. Now today, people have put kind of arbitrary delineations on them. Anybody remember Pluto losing its planethood at some point? That was kind of funny. So turns out that there's a number of objects that are roughly equivalent in size to Pluto. And when scientists kind of first realized this in the late 20th century, they were like, well, we can't make all of them planets. We have this really nice system where we just talk about, you know, these very concerted body. So they decided to draw a threshold right below Pluto in terms of its size and so forth. So it's a bit arbitrary in that sense, but there's a number of orbiting bodies. There's spherical bodies in the asteroid belt that look a lot like planets or moons that are orbiting the sun. It's a very squishy definition at this point, but I think it's thresholded based on size and mass at this point. So last I checked, Pluto is still not a planet, unfortunately. Sorry, Pluto.
It's just a small.
A little one, a dwarf planet, is that what they call it now?
Yeah.
Yeah, there's a number of those though out there, those trans-Neptune objects.
Because from what I remember, I was told that it becomes a dwarf planet and no longer an asteroid when its gravity is able to make it or like more actually spherical and drawing other objects of its scale.
Yeah, that one's a little bit tricky. Oh, I just realized we're about to go over here. I don't want to keep you guys. This has been a wonderful discussion. We'll pick it up right here next time. You guys have a wonderful weekend, and we'll do it all again on Tuesday or Thursday. Sorry, it's not weekend at all. I'll see you guys Thursday. Bye, guys. That one's tricky with the spherical thing. So we'll talk about that when we start looking at the asteroid belt, because there's some spherical ones there that couldn't have possibly become sphere-sized under their own gravity. And so you have to start, well, very few people are doing this, but you have to wrestle with a kind of metamorphic story for how they got to look the way they look.
Yeah.
Like, maybe they were bigger. Maybe they joined late to the party. Like, it's maybe there's processes we have no idea about. Yeah.
They were eroded like rocks and rivers.
Maybe, exactly. Yeah. That's an interesting hypothesis. Yeah. Then you have to somehow come up with a process out there in the asteroid belt that would pull that off.